Hi everyone, let's get started. So last class we started discussing language model and neural language model. We discussed statistical language model, Ngram, and then we also discussed RNN and CNN, right? We also discussed different issues of statistical language model. If you remember, we talked about long range dependencies, right? And we saw that if we use ngram, if we fix the count of, if we fix the value of n, then if two words are very far apart, you won't be able to get the dependency. The other problem is that in statistical language model, you always need to create this ngram table, right? If it is bigram, then a bigram table, and whenever a new document comes in, you need to recalculate all the bigrams, right, and repopulate the matrix again. Now, some of the problems can be addressed with neural language model. I mean, if you use CNN, for example, right, you also need to fix the window size, which is the size of your kernel, right, and then you I mean, if you want, you can apply multiple kernels, right, with multiple weight matrices and so on. The problem with CNN is that, again, fixing the window size is a problem, and if you increase the window size or decrease the window size, the matrix W matrix will be changed, right? The other problem is, again, the long range dependency can't be captured using CNN, because once we fix the window, everything within that window, all the words within the window basically act as a bag of words, right? So their locations don't matter as such, because if you change locations, you'll get same representation. Then we discussed RNN, which is a true sequence labeling model, where ideally you basically represent you process every token one by one. It's a temporal model, so the representation at the th time or the th location is ideally capturing the representation of all the previous locations, right? All the previous hidden states, ideally. So theoretically, RNN is able to capture the long range dependency, but empirically it is not, because we have this gradient, right, vanishing gradient problem and exploding gradient problem. Okay, and to address this, we talked about LSTM and GRU, where we use gated mechanisms to selectively identify which information needs to be propagated, which information needs to be stopped, and so on and so forth, right? So and GRU was just an extension of LSTM, where instead of using 3 gates, we use 2 gates, and then we don't have an explicit concept of cell state here. Hidden state basically acts as a cell state, and so on and so forth. So now we will see how we can use RNN, right? RNN can be LSTM, can be GRU. How we can use RNN for a sequence to sequence problem. What are sequence to sequence problems? For example, let's say you translate a English sentence into a Hindi sentence, right? Or let's say you have a long document, right, which is a long sequence, and you translate, or you basically summarize it into a small document, right? This is also a sequence to sequence problem. Sequence to sequence problems can be of 3 types, right? One is many to one, right, where your input is a sequence of many tokens and your output is a single token. Can you tell me an example of many to one? Sequence to sequence problem. Classification problem is not a sequence to sequence problem. MCQ is not a sequence to sequence problem. Summarization is many to many tokens to many tokens. Sentiment analysis is a classification problem, it's not a sequence problem. Now a token can be a A token can be a single word. A token can be a maybe an entity, right? Given a text, can we generate an image, right? So image is an entity, single entity, right? Of course, you can argue that an image can be represented by a matrix and blah blah blah, but image is an entity. Similarly, one to many, you can think of one to many problem as like image to text problem, caption generation, for example. Many to many problem, all the other problems are many to many problems, machine translation, summarization, and so on and so forth. Okay? So as you see here, there are two sequences involved, right? One is the input sequence, and there's an output sequence, right? And please try to understand the difference between a sequence to sequence, a sequence leveling problem, and a classification problem, right? So I'm talking about sequence leveling problem. So we will discuss different types of sequence leveling problems here and how we can model this using RNN. Okay, but as I mentioned in the last class, I will give you an idea of what's going on in the LLM world. So this is an update on August 1. So Qwen 3 Coder Flash was released in August 1. So it is claimed that Qwen 3 Coder is a is a better model with respect to other models, right? Other existing models. So it's basically a variant of Qwen 3 family. It has roughly 30 billion parameters, and it's a mixture of experts models. So 128 experts are there. Okay, and if you look at this blog here, you get an idea of all these performances and their benchmarking and so on and so forth. All right, let's come back to the actual problem. So sequence to sequence leveling problem. So let's say you are given a non-English sequence, right? And your task is to translate it to English, right? So what we do here is that we first use an RNN. Again, the RNN can be LSTM, can be GRU, can be normal RNN, vanilla RNN, and this RNN will be called as encoder RNN, right? So encoder RNN will encode every token. So this is my first token, this is second token, third token, fourth token, and the way we use RNN, the same way here also we use RNN here. So we get the representation, hidden representation corresponding to every token, and the last representation will be fed to the output, to the next RNN. So this is called encoder RNN, and similarly we have a decoder RNN, right? In decoder RNN, as you see, this is again RNN, so kind of similar representation, right? So when you train the model, during training you are given both the non-English sentence and the English sentence, right? And again here in the decoder state, for every decoder token you have a hidden representation, right? And the same way we essentially train the model. So what is the input to the decoder model? So this is my decoder RNN, right? And what is the input to the decoder RNN? Input to the decoder RNN is the final representation of the encoder, right? So as if the final hidden state knows about the entire input, right? So this will be fed to the decoder RNN, and the decoder RNN will basically generate something here. This will be fed as an input here. If you so again, there are two ways to do that. If you feed this as an input here, right? So then what will happen is that you are not able to feed the actual input to the RNN, right? So if you feed the actual input to the RNN, it will be called teacher forcing. Okay, in teacher forcing, your output will be fed to the decoder RNN directly, right? It is not the case that the output of every decoder state will be fed to the next decoder state. It is not the case. Okay, if you do that, then this will be a normal RN. This will not be a teacher forcing during training. But during testing, you will have to do that, because during testing you don't have the output at all, right? So during test time, you will have to feed the output of one state to the next state. Okay. Now you keep on doing this thing until unless you end up getting a token like end of a sentence, or some sort of delimiter, right? So, and how do you train this model? During training time. So how many parameters are there in this model? So in the encoder model, how many parameters are there? So I mean, if we ignore parameters associated with the embedding layers, if we just assume that embeddings are directly given to the RNN, we have only one parameter matrix, which is, let's say, WE, right? And how many parameters are there in the decoder? Two parameter matrices. One is WD and U. Because unembedding layer is also important. For every position, you produce the word, right? And how do you calculate the loss? So at every position, you will calculate the loss, cross entropy between the actual word which needs to be predicted and the word that you have predicted. For example, here at this position, let's say if you predicted I and you should have predicted he, so the cross entropy between I and he would be the loss here, right? And you essentially keep on adding the loss value at every state, and that's going to be your total loss. Okay, so the total loss will be this one J, and then you need to backpropagate this loss, right? Using what? Backpropagation through time, right? And this will be backpropagated end to end, meaning that all the decoder parameters as well as encoder parameters will be updated. So this will be backpropagated end to end. Remember, encoder model is not contributing to the error, to the loss. Only decoder model is contributing. Why? Because we don't need any output from the encoder model. But when we train the parameter, encoder parameters will also be updated. Why? If you do not update encoder parameters, you won't be able to see the alignment between two languages. We need an alignment, right? I am going to school, मैं school जा रहा हूँ. So we should understand that the model should understand that I corresponds to मैं, right? Going corresponds to जा रहा हूँ, and so on and so on. Okay, so now this is RNN. This is sequence to sequence model. Now, what are the problems in sequence to sequence model? What are the major problems? The first major problem is called the bottleneck problem, right? What is bottleneck problem? The bottleneck problem is that this hidden state has a lot of responsibility to remember the entire encoder, the entire input. And you all know, if the size is if the length of the input is long, then the last state, the final state will start forgetting about the states which are earlier. So this has a lot of responsibility. Therefore, there is a bottleneck. And the other problem is still there. What's the other problem? The other problem is that you can't process tokens in parallel. That's the problem of RNN, right? To address this, we will discuss. So to address the first problem, the bottleneck problem, we discuss a mechanism called attention. Okay. Now, what is attention? Attention is just a shortcut to access all the encoder states from the decoder states. Let's say this guy wants to access the encoder state. Now, if you use this framework, when you are at this position, this guy has no idea about this hidden state at all. Right? Because they are very far. Now think of a case where every decoder state has access to all the encoder states. right? And the access to the encoder states are dependent on decoder state. The way I access is dependent on the decoder state itself, right? Then we can address this bottleneck problem, isn't it? Right? So this is attention, and let's see how we can. What's the vanilla setup? What's the default setup of the attention mechanism? So हम बाजार गए थे. So this is the input. This is my encoder model, right? This is the first decoder state, right? The first decoder state, what is the input to the decoder state? Is the start token, right? Now what I do, now this decoder state will attend to all the encoder states one by one, right? What does it mean? It means that this state will try to see how similar the decoder state is with respect to other encoder states. Okay, so now remember, this is a vector, right? And all the hidden states are vectors, right? So what we do first, we first take the dot product between the decoder state and each of the encoder states one by one, right? And this dot product is called attention score. So you see this number, this value. So this is basically a real number, a dot product between this and this, right? Dot product between this and the second hidden state, second encoder state, third encoder state, and the fourth encoder state. What does the dot product mean? A dot product indicates the similarity between two vectors, right? So it will, the attention scores will give you similarity between the decoder state and each of the encoder states, right? So after attention score, what we do, we will pass this attention. So you can think of this as a vector, okay? But there is no guarantee that dot product will lie between 0 to 1, right? So what we do, we pass it through a softmax and we get a distribution. And this distribution is called attention distribution, right? We all know softmax, e to the power x by sum of e to the power x, xi. So we get a distribution, right? Now so if you look at the entry in the distribution, you see that for the first position of the decoder, right? Let's say this is 0.8, this is 0.01, let's say this is point something, right? Let's say 0.05, and so on and so forth, right? It means that with respect to the first decoder state, the first encoder state is more important. In order to produce the first output here, first token here, you should look at the first token of the encoder state, right? Probabilistically. So from the attention distribution, what's the next stage? From attention distribution, what we do is that this attention distribution will act as weights. Let's say this is 0.8, let's say this is 0.1, 0.05, 0.05. Okay, and this is my hidden state, H1, H2, H3, H4. There are 4 hidden states, right? So once we obtain the attention distribution, what we do, we take the weighted sum of the hidden states, right? And weights will come from the attention distribution. So weighted sum. So this will be 0.8 into H1 plus 0.1 into H2 plus 0.05 to H3 plus 0.05 to H4. And it will produce what? It will produce a vector of size same as the hidden state, right? Let's call it as H dash, right? So H dash is called attention output. Now please remember the terminologies. Attention scores are the dot products, attention distribution is the output after softmax, and then attention output. So what does this attention output mean? The attention output indicates a summary of the input states with respect to the decoder state. It's a summary. It's a summary of the encoder states, right? With why I said with respect to the decoder state, because the weights are calculated with respect to the decoder state, right? If I change the decoder state, the weight will be different. So then what we do? So if we did not have this attention mechanism, what we have done previously, we basically fed this to an unembedding matrix, and that would produce a distribution here. But here what we do, here instead of feeding this to the unembedding layer, what I feed H concatenation of U let's say this is decoder state D1. So D1 concatenation of H dash, right? I will concatenate the attention output and the first decoder state representation, and then I feed it to U. So the size of the U matrix will increase. Okay, and then we follow the same process. So now every decoder state has a direct connection with all the encoder states. Similarly, I will do for the next decoder state. You see here, after attention score, when you get the attention distribution, now this weight is high. That means this guy is more important to generate the second token of the decoder state, right? Similarly for third, fourth, fifth, sixth, and so on. Right? Now tell me how many extra parameters I have included, I have considered extra parameters in computing the attention score, attention output. What are the additional parameters I need to learn? Forget about you okay, I understand, but so you will increase as a byproduct of this, but any other explicit parameters I have considered? No, right? That's the beauty of attention. Now, of course, this is a vanilla version of attention. There are advanced methods where you can include more parameters, but in a vanilla setup, there is no additional parameter that we include. So with the attention mechanism, we now have addressed the problem of bottleneck issues, right? Okay, so attention is great. Why attention is great? Because now with attention, we can now we have access to many more information. For example, using this attention distribution, you can say, I mean, you can think of this attention, the entire attention distribution for all the tokens, right, as a matrix like this. So let's say this is your input, right, and this is the first output token, and these are the corresponding attention distribution. This is the second output token from the decoder, and these are the attention distribution. Third output token and the attention distribution. Now from the attention distribution, you can align two languages. You can say that, okay, he is more aligned to the first token of the input because the probability is high. With a pi, these three tokens are more aligned to the last token, right? Me is more aligned to the third token, and so on and so forth. So if you go back to the statistical machine translation era, right, before this attention mechanism came in 2014, 2015, before that, so statistical machine translation had a long history, 20, 30 years, 40 years. People had been trying different approaches, and one of the modules of statistical machine translation was how to align two languages. Right, you can translate every word to, so you can translate things word by word, right? If you have a dictionary, you can translate things word by word. But then how do you align? Let's say I am going to school, I am, I don't know, going, ja, raha, right? School, etc., etc. And then how do you align them? Because it is not a one-to-one correspondence, right? But after attention, people realize that you do not need an explicit alignment as such. Attention can take care of this, right? The second good part about this model is that attention provides some sort of interpretability. Although there are many papers which argued against this statement, but people still believe that attention will give you some interpretability of the model. Attention helps address the vanishing gradient problem. Why? Why? Because now you have direct access from decoder to encoder. The gradient can flow from decoder to encoder directly. The gradient may not need to pass through the normal sequence, right? And so on and so forth. The other beauty about attention is that it's not the case that attention is only applicable to encoder decoder. Attention can be applied to normal RNN, a single RNN. How? Let's say so this is my RNN model, right? So in sequence to sequence, you need two RNNs. Let's assume that you have only one RNN, right? How can we use attention here, right? So, I mean, here also you can say that, okay, this guy can attend to this. This can attend to this and this, right? This can attend to this and this. In fact, this can also attend to this. Can it? Can this guy attend to this guy? No. Why? It's a temporal model. It's a sequence model. When you have generated this state, right? When you are planning to generate this state, you don't have any idea about this state, right? So forward dependency is not possible. Backward dependency is possible. But anyways, I mean, attention can be used in normal RNN setup. Okay. So I mean, basically, if you look at it very carefully, attention will give you a summary of your input, right? And it will always give you a single vector, irrespective of the length of the input, right? If the length of your input is 4 tokens versus 10 tokens, you will always get a single attention vector, isn't it? Because ultimately it's a weighted sum. So attention doesn't depend on the input token. Okay, so it has many advantages. Now we'll move to the other part. So we have addressed the bottleneck problem, but we have still not addressed the problem of parallel access to the tokens, right? So we will discuss another mechanism called self-attention. We'll see that self-attention can address this problem. But before that, let me maybe spend little bit more time to again explain some of the important terminologies here. So we have seen that for every decoder, so every decoder attends to each of these encoder states one by one. So in self-attention, we will use 3 terms: query, key, and value. I would like to introduce these terms here only. So the decoder state is called query, right? And each of these encoder states are called key. Okay, and when we take the dot product between encoder and decoder state, it is basically a dot product between a query and key, right? So query, key, dot product here. Then attention distribution. After attention distribution, what we do? Weighted sum of all the encoder states. Now ideally, in a vanilla setup, in a regular setup, we take the weighted sum. So in a vanilla setup, we take the weighted sum of the keys itself, right? But if you have more data, you can also think of another term or another entity called value. What is value? So ideally, attention output should be the weighted sum of values. But in our case, values and keys are the same. in the normal RNN setup, in the normal attention setup, values and keys are the same. But later on, we will see in self-attention, we introduce an entity called values. We'll first take the dot product between query and key, then we generate the weighted sum of values. Okay, remember these terms, and I will tell you the meaning of query key and value. Why? You can relate query key value with the information retrieval perspective, right? Yeah.
Instead of taking the weighted max pool, because
max pool.
Meaning of
no, if you take the max pool of what?
That is having values.
No, then what? Let's say let's say you take this one.
Yes.
Right, and the value is 0.9, and then you multiply 0.9 with all the. Then what you do?
Only one given state.
So you will take 0.9 into H2. So then you don't have access to access to other representations, right? Remember, in any alignment, right? Token to I mentioned already, in any alignment, token to token correspondence is not explicit. For example, I am going to school. मैं school जा रहा हूँ, right? Am going to correspond to what? जा रहा हूँ, right? So it is not that only one token corresponds. One token contributes to the generation of the other token in the decoder. So in other words, in other terms, basically all the tokens are contributing in some ways. So it is important to consider all the tokens. Yes. Okay. Any other question? Yes.
So we had in the normal part, we had this distribution.
Here also have you. Here also have you. I mentioned, right? I mentioned here.
So
This is U. And the input to the U, earlier it was only D1. Now the input is D1 concatenation H1, H dash. Okay. Any other query? All right. So let's move on. Now there are different variations of attention. So I talked about this one. This is called dot product attention. You just take the dot product between query and key, right? You can also think of advanced attention mechanisms where in the transformer paper, what they have considered, they have taken the dot product and they have normalized this with the size of the key, square root of the size of the key, right? Why? I don't know. They mentioned that if you do that, it would help stabilize the process and so on and so on, right? You can also think of, if you have more data, you can also add a new parameter matrix W. So query is coming from here, key is coming from here, and then parameter matrix here, you project query and key through this linear projection, right? If you have even more parameter, you can also incorporate two parameter matrices. For example, what you do here is that you first concatenate query and key, right? You are not doing any dot product. Just concatenate query and key, pass this concatenated vector through W1, which is a linear layer, right? Then followed by some nonlinearity tan H, and then again you pass it through another layer W2, because you have a lot of data, right? So there are different variations of attention. Okay, so again, so the problem here is that attention is not able to address the parallel processing of tokens. We'll discuss self attention and then transform. Okay, all right.